Your support helps us bring you programs you love. Go to WyomingPBS.org, click on Support, and become a sustaining member or an annual member. It's easy and secure. Thank you.
Scott Acton graduated from a small-town public high school in Wyoming, and he took his first physics class at a community college in the state. This year, he's completing 24 years of work as a crucial team member in the deployment of the $10 billion James Webb Space Telescope. We'll talk again with Dr. Scott Acton. I'm Steve Peck of Wyoming PBS, and this is Wyoming Chronicle.
Funding for this program is made possible in part by the Wyoming Humanities Council, helping Wyoming take a closer look at life through the humanities, thinkwy.org, and by the members of the Wyoming PBS Foundation. Thank you for your support.
When I ask a person, what do you do for a living? What's your line of work? A lot of times that answer is pretty easy. Well, I'm a nurse, or I'm a police officer, or I'm a cowboy, or a firefighter, or a school teacher. If you were to be asked that question, what would you say you do?
I tell people I'm a scientist.
A scientist?
Yeah, I like the way that sounds.
Your career's had some interesting variety to it, but for a long time now, your primary focus of your career has been on one project, the James Webb Space Telescope. What is that exactly?
Yes, indeed. I started working on that in 1998, believe it or not, out of my garage in Hawaii, and decided that I would pursue that project when we left the Big Island. And I had no idea that I would end up spending 24 years, nearly 25 years on this project. But that's what it has been. I forgot what you asked. What did you say?
That was it. What is the James Webb Telescope?
Yeah, well, this was, everyone, of course, is familiar with the Hubble Space Telescope, or I think most people are. Yeah. And this can be seen as a successor to that. It doesn't replace the Hubble, because the Hubble is still in space and will be there for a long time, and plus they're looking at different things. But it supplants it, it complements it. This was envisioned, I guess, there was a meeting in roughly 1989 at the Space Telescope Science Institute where people got together and they discussed what the next big telescope would be. And they came out of it with a proposal for an 8-meter telescope that looked in both the ultraviolet and the visible and the infrared and pretty much did everything, but then soon came to realize that was impossible. But ultimately settled on a 6.5 meter diameter mirror, and something that would be half the weight of Hubble and half the cost and all these things. And of course,
didn't quite work out that way in every respect.
Didn't quite work out that way in every respect, but certainly technically speaking, everyone said it was impossible, and I would have been one of those people. But in fact, that's exactly what we've done. We've got this thing to work, and it works well.
Is it one of those cases where you were imagining you'd have to invent technology in order to do the thing that you were imagining?
Yeah, we didn't have to imagine it because it didn't exist.
Did not exist.
The actuators that move the mirrors didn't exist. They had to be invented. There was nothing like them until it was. The science, just the algorithms, to tease the misalignment errors of the telescope from the images that you take and figure out how to correct them, that didn't exist. Many of the technologies, how do you deploy that sun shield? If you've seen any pictures of how the sun shield's the size of a tennis court, and of course it was all folded up on launch. Just how do you deploy that thing? How do you deploy the secondary mirror, the primary mirrors, and all that had to be worked out, and sure enough, it was done.
The telescope was launched from Earth on what day?
On Christmas morning. Yep.
That was done by coincidence or design?
It was coincidence.
Really?
It was, I think, under a less pressure situation to get the thing up. They may have skipped Christmas Day and done it the next day, but as it was supposed to be done before Christmas, but when Christmas came and that was the next day up to launch, they went ahead and did it. I thought it was a nice surprise. I was sitting there with my family and at the kitchen table, and 5 minutes before launch, I spilled my coffee on the computer keyboard. and normally my family is quite vocal, but everyone at that moment knew not to say a single thing. Really? We calmly wiped it up and we waited and we watched it.
You were sitting at your kitchen table where?
In Niwot, Colorado.
How momentous was the day of launch
I guess for me it was mostly excitement. There were people who were not feeling excited in that moment. Here's a good example. Everyone, of course, knows about the Apollo program, and when the astronauts, Neil Armstrong, Buzz Aldrin, set foot on the moon, and they were jumping around on the planet, having fun and playing and singing. You remember that video? Sure. And everybody in the world loved that except for one person, the guy who invented those spacesuits. And he was dying. He thought they were certainly going to break something, and it was just going to be the end of everything from his perspective.
So you didn't have anything to do with propelling the
That's right.
ship off the ground.
Yeah, that was that was the European team's launch vehicle, the Ariane 5. Incredible vehicle. I believe they've now done their close to their last launch. They're moving on to the next version.
Where is it? How far away from Earth is it?
It's 1 million miles from Earth at a magical place called L2.
L2.
Yeah, it's sort of a loophole in the whole, gravity problem. You don't want it to be anywhere near the Earth or the Moon for that matter. And obviously it's got to be facing away from the sun. But if you get it, say, 1 million miles away from Earth, which you really need for it to get cold and for it to not have the light pollution, you don't want it to drift away forever. So there is a spot 1 million miles away from Earth where, by and large, with a few occasional course corrections, it will stay there indefinitely. And that's what L2 is. It's sort of a little gravitational hole where things, at least in one dimension, they tend to move to this point.
Because as I understand it, in other orbits, the process of orbit is a gradual falling almost.
Yes, that's right.
Leads to orbit. Here's a place where that does not happen or
well,
barely
yeah,
happens.
from the perspective of the spacecraft, it's still falling.
Yeah.
I mean, if you were there would be no gravity. You would feel 0 G.
Yeah.
But it goes more, we're not at that point. We're actually orbiting about that virtual point. So it's as though there were a planet there.
I see.
But it's not.
Yeah. I've heard you say that it represents the biggest advancement in astronomy since Galileo.
Well, Galileo is credited with inventing the telescope. He didn't. He copied the design from someone who made a much more inferior design, and in fact, you can actually still go see Galileo's original telescope. It's in a museum.
Is there anything about the James Webb Space Telescope that harkens to that still, or is it completely a relic of history now?
Well, the one thing we share in common is if you look at what Galileo did to the astronomy world in that moment, we are making a similar advancement now. I would think it's safe to say that this will change astronomy more than anything has changed it since Galileo.
More than the Hubble did, for example?
Oh yes, yeah, absolutely.
Why is that? What can we do with James Webb Space Telescope that we can't do with Hubble?
Well, it's looking at, again, they're looking at slightly different problems, but what the James Webb Telescope allows us to do is see into the infrared, deep into the infrared wavelengths. It's quite a bit bigger than the Hubble telescope is, and is quite a bit more sensitive, but most importantly, it's cold. The entire telescope is passively cooled to about 40 degrees above absolute zero. And so since you're looking at infrared, as you know, anything with the temperature, your body, puts off infrared light. So if we didn't have a cold telescope, the detectors would see the light from the telescope. And so instead, they can see a very, very distant galaxy or something that's emitting in those wavelengths.
At one point, you're describing the day and the recent moment that the first image from the telescope that you were hoping to see in the way that the telescope was supposed to work had been seen. You people of science are all slide rules and scowls and passive people. Did that get to you in any way?
It did. It was actually a very, very moving experience, and I would say actually the realization that these images were going to have so much content in them is what really got to me. It was if I could, the spacecraft, when you take a series of images, it all runs autonomously. You upload a program and say, we want to do these observations, this observation. So it takes all the images, and then when you have the opportunity, they're downloaded to the ground. But oftentimes, the last image that you take stays there in a buffer until you run the next program. So, well, maybe you don't want to wait for that last image to get done. So what you'll do is you'll throw a completely disposable, pointless image in the very last image in your sequence to flush that buffer out. And so what we had thrown was a simple image taken on the fine guider instrument, which isn't really a science instrument at all. It's just an imager that we use to stabilize the telescope, but you can also take a picture on it. But we downloaded that image, and when we looked at it, stretching the contrast in it, I realized that that single throwaway image had more than 500 galaxies in it. And that and the subsequent images that we took that confirmed this was an eye-opener for me. There were many astronomers that were saying, "Oh, of course you saw those galaxies. We never doubted it." Well, I didn't know that. I didn't know that they were just there. They've been there forever, or for all intents and purposes forever, and we just have never been able to see them. And just the realization in that moment, I remember talking to my wife about this, it was almost a religious experience. I don't mean in the sense of any particular religion, but just the knowledge that these galaxies are out there. There's no dark sky. Everywhere you look, it's galaxies. And I pictured, if you would just allow me a bit of poetic license here, I pictured them in my mind's eye as singing. I actually saw the galaxies as making a sound, singing, and not in any language that humans could understand, but clearly the emotion expressed was one of joy. And again, if I can push this poetic license thing a bit maybe even too far, I guess I see it as the universe being full of joy that we have finally got to the point where we can see, that we can look. It's like your child taking a first step. So that's what I'm going with. The universe is happy that we're looking at it.
I happen to be reading a book by an author named Niall Williams, and it's called This Is Happiness. And he lived in Ireland where it rained all the time, except he described the very occasional moment at night where the wind would be right and the clouds would part, and you could stand and look at the stars. And he put it this way: you see the stars in their infinity and their number, and the body feels small, but the soul feels huge, he said. And it kind of reminded me, I happened to have read that just a few minutes before I'd seen some of the things that you had said, and what you said it just now reminded me again. So there's more to you science types, you eggheads, than just the
I would say so.
You finally, I was thinking about looking at my basketball rim and thinking, I know that it's possible to dunk the ball because I've calculated it and I know that it could be done, but it doesn't mean I can do it. And you've said that you would prove mathematically that certain things would happen, but until you see it, it's not the same.
It was quite a worldview changing experience to see these galaxies. I'm not the same person before, and I obviously I don't care who you are, if you're a conservative fundamentalist, evangelical, young earth creationist, or whether you're an intellectual that just has a notion that maybe there's something beyond you, that seeing these images and understanding them will increase your faith in whatever God you have. Absolutely.
WyomingPBS viewers who may have recognized you from a couple of previous appearances on our channel would be interested in hearing again just a tiny bit about your educational background, and in particular the moment at which you took your first college physics class at Central Wyoming College. You didn't enroll at MIT or Caltech out of high school. You came to Central Wyoming College and you had a physics professor that, through a sort of coincidence of events, was able to give you an educational experience that was foundational for you.
It was, and the main thing he did was allowed me to do experimentation and kind of had the run of the lab there, but he encouraged me to leave and go to the University of Wyoming.
What was his name?
Johnson, Professor Johnson.
And as I recall, there were a couple of people there were a few more people in the class at the beginning, but gradually it came down to where much of the time you were almost working in sort of a one-to-one practicum with him.
Very true. We had very small classes here. There were 3 of us in that physics class, as I believe. There were as few also in my calculus classes. It was a good experience. Maybe not for everybody, but it was important for me. I'm very glad that I didn't step right into a university out of high school.
You've gone to some lengths to publicize your work and the work on the telescope.
As I said, I've spent almost 25 years in this project, and nobody in the beginning predicted it would have gone on that long, right? Well, it turns out that the stuff I've been doing didn't take exactly 25 years. So we finished our part of the subsystem several years ago, and obviously you can always improve it. I mean, they're still improving tide, right? Yeah. So, but by and large, we were mostly done, and I found myself in a very unique situation. My children were out of the house, either going to college or often being married, and I was, getting up there in years, but my body hadn't figured it out yet. And we had this spot on the project for over a year where I didn't matter anymore. So I decided to do something that I have always wanted to do, which is try to bicycle around the world, or more or less around the world. And when you bike around the world, you have to do it for something. You have to have a cause, because not everybody understands why you would just hop on your bike and start pedaling, right? You have to have a reason. Well, world peace was taken. So I decided to bicycle around the world to promote the James Webb Space Telescope. And I formed the James Webb Space Telescope World Bicycle Tour. We got jerseys, I got a website, I got sponsors.
I have one of those.
Yes, we do. Got business cards, and I got this little pain in my chest whenever I started out on a ride.
Uh-oh.
And you of course know where that went. Come to find out, I had some heart issues. I had to have surgery, which set the ride back quite a bit, but I survived that, and we got on the road, and I spent about a year pedaling through many different countries, and I'd stop about every week or so and give a talk. Mm-hmm. And I encountered a lot of people in a lot of different places. They were all very, very interested in the telescope, and it was quite an experience. I still keep in contact with many of the people that I've met. Not everybody is interested in astronomy, but I think almost everyone's interested in technology. Mm-hmm. And the telescope, like I say, represents probably the greatest technological achievement. There's more man hours in this than there were in the pyramids, or I've heard that anyway.
I remember reading once about the construction of the Transcontinental Railroad, and the workers were trying to tunnel their way through the Sierra Nevada range. And in some cases, the rock was so hard that they'd work an entire 12-hour day, and at the end of it, they'd made a 2-inch indentation that was about that big around. But wow. One of these guys said, but it was progress. We could chart what we did. When you're on something for all these years and doing work that I don't understand, but I imagine is very calculated, trial and error, experimental, observational work, how do you chart progress in it?
Yeah, that's a good question. Well, we have milestones. Mm-hmm. We have objectives and requirements, and you measure your progress against those. Requirements
set by?
So we knew very early on what the basic architecture of the observatory would be. 18 segments, deployable, and we knew what kind of adjustments we could have on the individual mirror segments and the secondary mirror and everything like that. And we knew basically what the performance would be of the science instruments. So the goal is, how do you align the telescope? And so at the beginning, we didn't know how. In the end, we did. So that basically, and of course, we build computer models of the observatory. We commissioned this telescope end to end 100 times in a computer model before launch. And those models are set to be slightly pessimistic, intentionally, to make it a little harder than it probably will be. And when we could reliably, let's say 95% of the time, get through the process without a failure, then we knew we were guaranteed at least 95% of success.
And when you're talking about making these adjustments to the individual segments, they're small.
They're
right?
Really small, yes, very, very small. You don't think of it that way.
You're not turning a knob and watching the mirror do this.
No, there are some moves that happen that are fairly large. Obviously, the deployments. Is, if you've seen the animations, the secondary mirror is actually folded up behind the primary mirror, and then it flips out, I don't know how it's like kind of an arm unfolding. Mm-hmm. And so that's a big move. And then the mirror segments for launch are actually held back against the structure, so they're not shaking around. And they had to be moved about 12 millimeters out. So that's the normal deployment. But from that moment on...
12 millimeters constitutes a big movement.
Well, that's, enormous. That took a week. These mirrors move slower than grass grows. And to prove this, one of our team members made a chia web, a little brick thing the size of the shape of the Webb primary mirror, and put chia seeds on it and watered it. And as we deployed the mirrors, we could see, sure enough, that grass was growing considerably faster than the mirrors were moving. So, yeah, but when we make an adjustment, we typically are talking about nanometers, not millimeters, so not even a millionth of a meter, but a billionth of a meter.
Billionth of a
Yes,
meter.
nanometers. A handful of nanometers.
You mentioned that you set some somewhat pessimistic objectives, but when you finally got these first images, they outperformed the model.
Yes, they did quite a bit. I want to be careful about what I say in terms of actual requirements and stuff, but in terms of how badly the mirrors would deploy, we were much better in practice. It turned out to be much easier. Just the job of finding where the telescope is pointed. You think about it. If you're looking through a soda straw and you don't know where in the sky you're pointed, you could look around forever before you find a star you recognize. Well, we were right on, absolutely right on. The mirrors weren't all spread out all over the place. They were fairly tightly packed when they deployed. So all that was quite a bit easier. But most importantly, though, is we were able to align them without them running into each other or running out of rooms between them. So as a result, the actual, we call it a wavefront, so the actual quality of this aligned telescope was considerably better than the threshold we set for ourselves.
Building of the telescope was, it seems to me, almost an industry unto itself.
Yeah.
The sheer volume of individuals and processes and components and labs and companies and states of the union and work sites, and a huge enterprise to be a part of.
Thousands of people were involved in this.
And how many individual segments were there, did I read, or processes, I hope I'm not using the right terminology, I'm sure, which could have gone wrong?
Oh, yes. There were so many things that could have failed, but they got a lot of attention. In my own mind, our program manager, Bill Oakes, was on 60 Minutes shortly before launch, and he said there was a 100% chance it was going to work. He's 100% certain, and he was right.
He was right.
That's right.
That's what you want in your program.
I was, in my mind, I guess I sort of, because you have to emotionally prepare yourself.
Sure.
In my mind, I was thinking maybe 70% chance of success. That's just because of those many things, things that had to deploy release mechanisms. You have something, you don't want it to be loose for launch because it would be destroyed, so things are holding it down, but you want it to let go. Well, those, you can't test them. You have to just build them and build them right. But they all worked. Every single one of them worked. I tell you, the amount of confidence that people had in me was humbling and terrifying.
Well, you mentioned a time where you actually personally had to make some calculations when the process software,
yes,
you didn't have confidence in those.
It had to do with initially the telescope wasn't pointing as well as we had expected it to, and they eventually figured all that out, and it now points perfectly, but at the time it did not. And the software had assumed that it would. And so the calculations to bring the mirrors from their deployed positions, spread out all over the sky to a common point had to be done by hand. Wow. And I remember walking home just really, really nervous that the commands that I just told them to apply to the observatory wouldn't just, would actually work. And I was talking to my wife and she said, "Scott, that's why you're there."
That's why you're there.
That was her loving way of telling me to cowboy up.
And you did. When a mail carrier has decided to retire and he puts his last envelope in the last mailbox in his last shift, he knows he's finished. When did you decide or realize, or was it determined that your work on the telescope was done?
It's a very difficult or an interesting emotional perspective, but obviously I've seen this coming for 20 some odd years, and it's almost like you're climbing a mountain and it's fun, right? Everybody likes to climb a mountain, and you have this objective, you've got to get to the top. And when you finally get to the top, there's this tremendous sense of peace and sense of accomplishment, but you realize that you've just destroyed that which was giving you pleasure. So now what do you do? And I feel very much in that situation, but of course the challenge is to move on to the next thing, and this is what we all deal with these kind of things. And so for me, I'm looking at opportunities within my company and without. And the world record for the oldest person to bicycle around the world?
56?
Yeah, 56. 56.
Whippersnapper.
I could have done it on a unicycle at 56. Who knows? Maybe there's another bike ride coming in the future.
I've observed with interest at that time and through the years that you've had many other things that you've done besides hard calculating science? I mean, you've been involved, we talked about your physical fitness and your cycling, and you're involved in music and in drama and speech and debate, and an engaging and highly capable writer, I know. Has that been a conscious sort of thing that you've done? Well, I want to make sure that I spend my life doing something more than intensely commissioning the James Webb Telescope. Or is it just the way you are, the way it's worked out?
Yeah, I would love to say it was due to discipline on my part, but I don't have any discipline. It's just the way it worked out.
Yeah.
Yes, absolutely. You mentioned drama and speech. I would say the most important class I took was, of course, Mrs. Sackman's speech class. The ability to communicate, hands down, yeah, ability to communicate and express yourself, that will serve you better than any calculus class, any math class you ever take.
You compared the expenditure of tax money into the space program to some consumer product. And I think it was something like we spent more money on potato chips last year than we spent on the space program. What's your point in making that comparison?
Well, we don't, I mean, oftentimes what people will say is that, well, why don't we spend this on feeding starving children? And, you know, the reality is that, you know, okay, I suppose if the people I work with, if it came down to building this telescope or feeding starving children, we would feed the starving children. But the reality is nobody ever gets to make that choice. Nobody has asked that. The fact that we're doing these things is because it's a reflection of the national will of the United States, and in this case, our world partners. This is what people want to do. But yes, it's not very much money. It's a blink of the eye in terms of federal spending. And I think it was well spent. You know, I know that there's a lot of controversy about the cost of the telescope.
Which ended up being?
About $10 billion.
$10 billion with a B dollars.
With a capital B, yeah. And, but you know, that was stretched out over 20 years, so which is part of the reason it costs so much. I mean, but it's not really very much, and I think it's going to be a bargain when you see the science that comes out of this. It is going to be unbelievable.
There's a kid in Wyoming somewhere today who's in an 8th grade math or science class somewhere who sees you and might want to emulate or think about emulating what you've done or something like it or something beyond it even. What do you tell that kid? What should that kid be thinking about?
You should give me a call.
Give you a call.
Absolutely. I have, you know, the people that, like myself, I'm a scientist, people throughout the world, you know, if you were just to write a letter or somehow get in touch with someone, if you want to be like that person, say, "Dear Dr. So-and-so, I dream of being, you know, the kind of person you are. I really like this stuff. I find this interesting." And you can't wait till you're a senior in college because nobody believes you then. But when you're in an 8th grader, like the example you put, if you write a letter, say, I stay awake at night dreaming about what it would be like to be working in the field you are, and send that to that person. I don't care who you are, where you live, that scientist or professor or researcher will leave tears on the letter. All the times and all the talking that I've given, you want to know how many times someone has written me a letter like that or contacted me for that? 0. Wow. That has never happened. I gave this similar kind of talk to at a university once, and said that nobody had ever contacted me. And right after that, 30 people in the audience, they're all physics majors, and one guy ran up to me and said, "Dr. Acton, I would give anything to be able to work and do what you're doing," and I hired him.
Really?
Yep. So yeah, absolutely. I tell you, the opportunities are there. Particularly, you don't think that's the case, but it is. Who is it? Woody Allen that said that 80% of success in life is showing up, and I believe that. If there's something you want to do, if you will, as a young age, if you will reach out to those individuals, you will find people bending over backwards to help you, because it just never happens. Never does.
Scott, it's good seeing you again.
It's great seeing you too, Steve.
Thanks for being with us on Wyoming Chronicle, and I know you'll make a success of your next thing.
Thank you.